So in this video we're going to talk about tangent, the last major trigonometric equation. And before we get into this, you want to make sure you really understand sine and cosine. So you want to be able to answer this question. Which will produce a greater number, sine of 30 degrees or cosine of 30 degrees? And you want to be able to explain why, because that's how you really show that you get something, if you're able to explain it to someone else. So remember, sine just means the opposite side of some angle of focus, in this case are 30 degrees, divided by the hypotenuse. It's the opposite divided by hypotenuse fraction for some angle. So in this case, our opposite's length is this, and our hypotenuse's length is this. So that's going to be some fraction. And looking at our cosine, cosine is just the adjacent divided by the hypotenuse. So notice how my adjacent is much longer. It is getting divided by that same hypotenuse. So because my adjacent is longer, it's going to be a bigger percentage, a bigger fraction of my hypotenuse than my sine is. So cosine of 30 will actually be bigger, and I can check on my calculator. And we can see that this is true. So if some of this stuff doesn't make sense, you might want to go back a video or two and review sine and cosine. So in the last two videos we saw how Pythagoras built up an opposite divided by hypotenuse concept. That was just sine. And we also saw how he built up an adjacent divided by hypotenuse concept, which he just named cosine. So Pythagoras was thinking, I may as well just look to see if there is an opposite divided by adjacent fraction pattern going on as well. And long story short, there was. What Pythagoras discovered was that every angle has its own constant opposite over adjacent fraction. So for instance, a 16-degree angle will produce an opposite over adjacent fraction of 0.287. So no matter how big or how small your right triangle is, or no matter if your right triangle is tilted or flipped or anything like that, as long as you're focusing on an angle of 16 degrees, you know that the opposite of that 16 divided by the adjacent of that 16 is equal to 0.287. And again, like we talked about in the last two videos, another way of looking at this, the opposite will only be 28.7% of the adjacent. And you can see how small that opposite is when compared to the adjacent side to verify this statement here. It should make sense. So this stuff shouldn't be too hard to digest if you really understood the sine and cosine conversations we had in the last two videos. And just like we talked about, Pythagoras had discovered that the opposite over the adjacent of a 16-degree angle will always equal 0.287. He also wanted to find out what the opposite over adjacent fractions were for all the other angles that he could. So he carried out this experiment here a bunch more times to figure out those fractions. And soon enough, he had a long list. So here's our new list with our sine and cosine lists. Notice that in the beginning, our opposite over adjacent fractions are very similar to the sine fractions. They're both yielding pretty small fractions. And the reason for that is that when you have a small angle, like we talked about in the previous two videos, a small angle will produce a small opposite, very, very small number here, and a big adjacent. So a big number in the denominator. And we know that a small number divided by a big number is going to be small fractions, small decimals. But look at what happens for big angles. We're getting some weird stuff that we haven't seen at all in our previous two videos for sine and cosine. Remember, sine and cosine will always yield fractions that are less than 1. And of course, the reason for that is because the hypotenuse, my denominators here, will always be bigger than my numerators. But our new concept, opposite over adjacent, doesn't have hypotenuse in it. So if I have a big angle, I'll have a big opposite and a small adjacent. And this opposite here could be several times bigger than my adjacent. In the case of 80, the opposite is more than 5 times bigger than the adjacent, and for 85, the opposite is more than 11 times bigger than the adjacent side. So know that our new concept here, opposite divided by adjacent, is a bit different than sine and cosine in that for our bigger angles, after some point, we're going to get whole numbers. So of course, Pythagoras wanted to give this new phenomenon a name, and the name that he settled on was tangent. And we won't talk about why he named it tangent. That's really more of a calculus question. So of course, Pythagoras rewrote his entire list. So this is it. These three sort of equations here, sine, cosine, and tangent, are the most important things in trigonometry. So if you really understand these, you are well on your way to understanding all of trigonometry, because there's more coming. And you'll also be able to use these three equations to solve many engineering problems, and especially for mechanical, electrical, and civil engineering, you'll use these equations all the time. So now we'll solve an example problem using tangent. Alright, so here's our problem here. We're going to focus on our angle right here, our 28, that's our angle of focus, which makes this our hypotenuse, our opposite, and our adjacent. And now notice, to solve for the length of this unknown side, we can't just use sine or cosine here. We can't use sine to solve this problem because it doesn't have the adjacent in it, and we want to know how long the adjacent side is. We could use sine to find the hypotenuse side because we know that opposite to be 4, but that's not what the question's asking for. And we can't use cosine to solve the problem because we don't know the adjacent or the hypotenuse. So we have to use tangent to solve this. So I can use my calculator to figure out the tangent fraction, the opposite over adjacent fraction for 28 degrees. That's just 0.532. And I know that tangent is another way of saying the opposite over the adjacent of our 28, which we know is 0.532. Opposite is 4, adjacent is unknown. So doing our algebra, doing 4 divided by 0.532, we get 7.52. That's our answer. So now, because we know our adjacent, we can use cosine to calculate the hypotenuse, or we can just use sine to calculate that hypotenuse. Either one will work. So make sure you get plenty of practice using sine, cosine, and tangent to solve for the sides of a right triangle. That's really what it's all about. You want to use sine, cosine, and tangent to solve your problem in the least number of steps possible. So make sure you really understand sine, cosine, and tangent, because the next video is all about the unit circle, and we'll see how we'll build off of our knowledge of sine, cosine, and tangent to construct a new concept.